Welcome to your next AP mathematics lesson, and this one specifically deals with the number e. So the number e is one of those numbers that is a constant like pi. Pi rounded off is 3,14. Now you might have on your calculator, if you've ever gone through it, you might have gone and you might have seen right here at the bottom, there's a little number right there, e, which interestingly enough is also where pi is located. And then again, up on top over there, you've got e to the power of something. So you can very easily go and you can just press alpha, which gets you to that e, and you can press equal. And it gives you that the value e, which is a constant that never changes, is 2,718 if I round it off to 3 decimal places. So e is rounded off the number 2,718. Right. Now, the number e is an incredibly important number for calculus, and you will find it out as we go along. Now, initially, when the number e was found, it wasn't necessarily used in calculus. It was discovered by a mathematician by the name of Jacob Bernoulli, and he was investigating the limit of k tending towards infinity of 1 plus 1 over k to the power of k. Now, we're not going to go and do this entire thing, but I do just want to quickly show you this. If I want to go and I want to figure out what this is equal to, I can go to my calculator and I can type in 1 plus 1 over, and now please note, k is tending towards infinity, so this value is becoming infinitely big. And this value is k as well, so it's becoming infinitely big. So I'm going to go and I'm going to substitute k with 100, which isn't infinitely big, I agree, but it's relatively big. So I'm going to substitute 100 in there, and I'm going to look at the result. So the result there is 2,7048, which if you look at this and you look at that, you go, that's interesting. So let's see what the calculator can cope with. Let's now make that number 1,000, so we make it even bigger. Press equal, and the calculator gives me 2,7169. Now, we are going to run out of calculator memory soon, but let's just try and see if I make this 10,000, what does it give me? Look at that, 2,718. So the bigger and bigger that value becomes, the closer that it goes to infinity, the closer this goes to that e number. So this is how Jacob Bernoulli first found that number e, and later on it was used by another mathematician called Leonhard Euler, and he specifically used it in calculus. And we're now going to go and look at why was this used in calculus. Okay. Now, first things first, I can go and I can draw this graph, and this is the graph of y is equal to e to the power of x. So please remember, e is not a variable, e is a constant. E is the number 2,718. So if you want to think of it like this, imagine for a moment that instead of this being the graph y is equal to e to the power of x, this is the graph y is equal to 3 to the power of x, which if I round out 2,718 to the closest integer is then going to be 3. So that is then just a normal exponential graph, which will be exponential increase because the base right over there is greater than 1. So I've got that exponential increase. And I've put 2 points there. The first point is the y-intercept, which is the point 0, 1. And the other point is the point on the graph, which I get by substituting 1 in there. So if I substitute 1 in there, I get the point 1e. Now, they now ask the question, determine the derivative of fx from first principles if fx is this graph e to the power of x. Now, we are not actually going to do the full first principles. That is way too complicated. We are again just going to go and we're going to inspect what happens when I work out the first principles. Now, in order to do this, we are now going to go and I'm going to draw a tangent over there because that's what I'm actually trying to find out. I want to know what is the gradient of that tangent where x is equal to 1. And in order to do that, I'm going to go and continue with this first principles problem. And I'm going to say, this is then the derivative where x is equal to 1, which is equal to the limit of h tending towards 0 of, and if you recall, it's the f of x plus h. So the f of x plus h, if fx is equal to e to the power of x, is going to be e of 1 plus h. Because remember we said x is equal to 1. So normally we would put x plus h in there, but now we're going to put 1 plus h in there. Minus then the e of x. But again, I'm not going to use e of x, I'm going to use the e of 1 over here. And then I'm going to put this over h. Now, the problem with this is obviously the following. You can't go and substitute h for 0, because if you substitute h for 0, you're going to end up with a 0 denominator, which can't happen. But we can go and we can inspect what happens by making that h tend towards 0. So I want to make it smaller and smaller and smaller so it's closer and closer to 0. And again, I'm just going to use my calculator over here. So I'm going to say it's going to be e, and I'm going to use the e button over there, e to the power of 1 plus, and that h I want to make it tend towards 0. So I'm going to make it 0.001. Minus then e to the power of 1 divided by, and again I want h to tend towards 0, so I'm going to also make that 0.001. And look what I get over here, 2,719. You look at that and you go, damn, that kind of looks familiar, doesn't it? So let's make this value even closer to 0. So we go back to this and we say, we'll go back and we'll make this value even closer to 0. So I'll put an extra 0 in there, and I'll put an extra 0 in there, and I'll press equal again. And look at that, 2,718. So what we are effectively saying is we are saying this. This is going to be equal to 2,718, which means it's equal to e. So that means this point right there, if the x coordinate is 1, the y coordinate is e. But if the x coordinate is 1, the derivative is equal to e. So we are saying the gradient here of that tangent is also equal to e. And what this allows us to do, and this is a very, very important deduction, is it tells us that if f of x is equal to that function e to the power of x, then the derivative of fx is also e to the power of x. So this is very, very interesting, is the fact that this is the one function that if I find the derivative of the function is still equal to the function. Just like over here, when I substituted 1 into the derivative, I still got the function, I still got that e. So that is why this number e is so incredibly important for our differentiation section. Okay, now we will get to finding the derivatives of e, but that will happen in a later video. We are now just going to first play with this number e for a little bit, and we're also going to play with the inverse function of e, which you will see just now is also a very, very, very important logarithm. And it makes sense that it's a logarithm because this is an exponential function, and you have already learned this here in core mathematics that the inverse of an exponential function is a logarithmic function. So, next discussion, log and the number e. Now, you've done logarithms in core mathematics, and you've learned that if I write the log of x down, then if there's no base over there, the base is actually base 10. So on your calculator, if you look at this log button over there, that one specifically right here, if I type this log, then the base number that's not being shown is 10. And this is the way that John Napier, who invented logarithms, he decided that the base number of log has got to be 10. So because the base number of log is 10, I will then know that the log of 100 is equal to 2. Why? Because 10 to the power of 2 is equal to 100. So if I press equal, I go, yes, it's 2. But the problem comes with the fact that technically speaking, that base number of 10 doesn't help us at all when we get to calculus. So when we get to derivatives and when we get to integrals, the base number of 10 is absolutely useless to us. So what then happened was, they decided, specifically Euler decided that your natural logarithm shouldn't be log base 10x. Your natural logarithm should be log base e x. So this number e has now become the base number for my natural logarithm. And this has been defined as ln. So that is Ln, that stands for ln. And if you look at your calculator right there, you'll see ln appears right over there. So whenever I type in ln, it doesn't give me a base because the base is automatically e. And just to prove that to you, if I type in the ln of e, it's going to be its log base e, which is equal to 1, because e to the power of 1 is equal to e. So if I type equal there, you'll see this is equal to 1, because ln is a log with a base number e, and then log base number e is equal to 1. So that's why I've got that ln x is log base e x. Now, quickly we need to talk about the graph of y is equal to ln x, and that relates directly to the fact that ln of x is the inverse function. So inverse functions always reflect around the line y is equal to x, and it's specifically the inverse function of that graph we've just drawn, which is y is equal to e to the power of x, which has got a y-intercept over there, which is the 0.01. And that means if I now go and I draw over here the inverse function, which reflects around that line, then that is going to be y is equal to ln of x. And please remember with inverses, if I have a y-intercept of 0, 1, then over here I will have an x-intercept of 1, 0. So pretty much very, very important, ln x is the inverse function of e to the power of x. And this is going to be important for us later on when we do our derivatives and also when we do our integration. So please just remember that deduction. Now, because ln is a logarithm, all of the log laws that I learned when I was doing the log section is also applicable to ln. So what they've done on your information booklet, your AP Maths information booklet, is they've written the log laws like this. Instead of going log of base a x plus log of base a y, they've just gone the ln of a plus the ln of b, because remember, ln is a log. So according to the log laws you did at the beginning of the year, you can then go and say, but if I add two logarithms and the bases are the same, which they are, because ln means the base is e and ln means the base is e there, I can then go and say it's the ln of a times b. And this does appear on your formula sheet. And if I subtract two logarithms and the bases are the same, then it's going to be, in this case, the ln of a divided by b, which again, like I said, does appear on your information sheet. Then also, law 3 that you did in logarithms say that if I have an exponent up top here, I can move the exponent and multiply it by the entire log function, so I end up with n times ln of a. Now, this one particularly is my change of base law. So with my change of base law, I can't use ln, because the whole purpose with the change of base law is that you are now actually going to go and you're going to change the base. You might not want ln, which has got the base e. So please remember, I can change that base to whatever I want to have it. In this case, I'm going to go and say the base is b, as long as I divide by another log with that base of b, and then obviously this x will go top, and that old base, the original base of a, will go to the bottom. So those are my log laws as given on my information booklet. And just to show it to you, right over there on the information booklet, you've got those 4 log laws. So you have them in order to use them. Now, we do have a couple of more interesting deductions when it comes to these log laws. The first interesting deduction is this, and I will explain it a little bit further. It's not on your information booklet, but it is very, very, very useful to know this. The first deduction from your log law says, I can convert this to minus log of base ax, but I can also convert this to log of a1 over x. So if you look at that, log of 1 over ax is equal to minus log of ax, which is equal to the log of a1 of x. Now, in order to show you how this works, is actually very, very simple and straightforward. It all has to do with these 2 laws. So the first thing I can do over here is I can take that log 1 over ax, and I can break it up by using my change of base law. And I'm going to break it up into log of x over log of 1 over a. I don't really have to go and pick a specific base there. I'm going to leave it out, which means the base is 10. So now I understand that this is going to be log of a to the power of negative 1. And that negative 1, using this law, can just be moved to the front of the logarithm. So I can do this. And now I can put this back together again. Because please remember, this law doesn't just have to be used from left to right. I can also use it from right to left. So I can take the two logs and I can put it back together again as long as the bases are the same. So what I can do over here is I can then say, taking the minus over here, this is the log of base A x, which is I come up with this result. And then if I keep on playing with it, in other words, if I move the minus to the top and then make it the exponent of x, then I can come up with this result. But like I said, you can memorize this and you can use this. You don't need to know this proof at all. It's just important that you realize that I can change this. And just to show you on the calculator an example, if I go and I say the log of a half, 4. Now, the log of a half, 4, you should know, a half to the power of negative 2 is 4. So the result there is going to be negative 2. But if I now go and I swap these around, meaning I make this one 2 and I make that one a quarter, then that's what this deduction says. It says this should also be equal to negative 2. And if you think about it, of course it is. 2 to the power of negative 2 is a quarter. There you go. Or if I go back and I change this one to 4, but added to that, I put the minus in front, which is the same as this one over here, then again I go 2 to the power of 2 is 4, so this is 2, but then it's going to be negative 2. So all of these mean exactly the same thing. Right. The second deduction is a very interesting one. It says I can rewrite the log of base AB as 1 over the log of base BA. So if I go and I swap the base and the number around, I just have to make sure that I write the reciprocal 1 over, and this is equal to each other. Now again, in order to understand this, it's really not that difficult. If I take that log base AB and I break it up, and I say I'm going to break it up into log B over log A, then I can do the following. I can swap these two around. So I can make this the numerator, and I can make this the denominator, as long as I make it to the power of negative 1. Because you guys should understand, to the power of negative 1 means, whoops, it's on the wrong side, it should be back to that. Now, if I use that change of base law and I put this back together again, I end up with a log of base BA. But it's to the power of negative 1, which means it should actually be 1 over log of base BA, which is exactly where this comes from. So this is a very nice deduction. Again, you don't need to know this entire proof. You just know that I can swap the base and the number if I go 1 over. And the last little deduction of these log laws is a very lovely little one. This is just equal to x. So in order to understand this one, it's slightly tricky, but in order to understand this one, I think the easiest way is to say, if I go and I take this conclusion right there, or let's rather start with this, and I say let's make this equal to y. So let's set y equal to a to the power of log ax. Now if I use my log definition, I can take this exponent, which is my input, and I can make it my output, log base ax. But I'm only allowed to move this from the input to the output position if I write a log over here, because I need the inverse. And the base is a, the number is y, so from that you can deduce that x is equal to y. And because y is equal to that a log a to the base x, it means y is equal to x, which means that overall result is x. Again, you don't need to know the proof of that, you just need to remember this because it's a very useful deduction to have. So that's pretty much the discussion of E and the discussion of Lin, as well as our laws. In the next video, we're going to do some examples using E and using Lin in equations, in graphs, and also in word problems. So we'll do all the well, it's not really practical examples, but we'll do all the examples in the next video lesson. So thank you very much.